Hello and welcome back to Steven Data. Finally, in this video, we want to start learning probability officially. In this video, we will learn basic probability. In detail, we will learn interpretation and rules like equally likely outcomes, relative frequencies, probability of an event, and some other subjects along with some examples to catch them right. You will see the subjects in this video are very sensible and very easy to catch. But as I said before, I want to teach you the probability completely. Consequently, I have to spend a whole video on these easy topics. Okay, enough talking. Let's dive into the video to see what we can get from it about probability. Probability is used to quantify the likelihood or chance that an outcome of a random experiment will occur. For example, the chance of rain today is 30% is a statement that quantifies our feeling about the possibility of rain. The likelihood of an outcome is quantified by assigning a number from the interval of 0 to 1 or a percentage from 0 to 100 to our outcome, and higher numbers indicate that the outcome is more likely than the ones that have lower numbers. The probability of 0 indicates that an outcome will not occur, and on the other side, the probability of 1 indicates that an outcome will occur definitely. In fact, the probability of an outcome can be interpreted as our degree of belief that the outcome will occur. Thus, different individuals will no doubt assign different probabilities to the same outcome. For example, you may feel that the chance of rain today is 0.1, and another person feels differently and gives the probability of 0.6 to the rain today. This difference comes from many factors like experience, personality, domain of knowledge, and many other things which are not our subject. The probability of an outcome is interpreted as limiting the value of the proportion of times the outcomes occurs in n repetitions of the random experiment as n increases beyond all bounds. For example, if we assign probability 0.2 to the outcome that there is a corrupted pulse in a digital signal, we might interpret this assignment as implying that if we analyze many pulses, approximately 20% of them will be corrupted. This example provides a relative frequency interpretation of probability. After all this, let's talk about scientific probability. What I mean by the scientific is the probability that comes from a reasonable conclusion of a model, not humans' feelings. In the scientific world, probabilities for a random experiment are often assigned on the basis of a reasonable model of the system under study. One approach to calculate this number is to base probability assignments on the simple concept of equally likely outcomes. For example, suppose that we select one laser diode randomly from a batch of 100. Randomly implies that it is reasonable to assume that each diode in the batch has an equal chance of being selected. Because the sum of the probabilities must equal 1, the probability model for this experiment assigns probability of 0.01 to each of the 100 outcomes. As I mentioned, this example is a good introduction to a concept called equally likely probability, which says whenever a sample space consists of n possible outcomes that are equally likely, the probability of each outcome is 1 over n. It is frequently necessary to use this concept in situations where events are composed of several outcomes from the sample space. But there is an important point. This concept is straightforward for a discrete sample space, unlike the continuous one. But don't worry, I will talk about the continuous sample space later. Now, let's see a simple example. Assume that 30% of the laser diodes in a batch of 100 meet the minimum power requirements of a specific customer. If a laser diode is selected randomly, that is, each laser diode is equally likely to be selected, our intuitive feeling is that the probability of meeting the customer's requirements is 0.3. But is our intuition true? Let E denote the subset of 30 diodes that meet the customer's requirements. Because E contains 30 outcomes and each outcome has probability 0.01, we conclude that the probability of E is 0.3. And we can see that the conclusion matches our intuition, and our intuition was true. But to understand this concept better, let's see another example. We know that each numeral on a die is equally likely to occur when the die is tossed, and the sample space of throwing a die has 6 outcomes from 1 to 6. Thus, the probability of getting a chosen numeral can be calculated like the number of times the numeral occurs in the sample space over the total number of possible outcomes. So, the probability of getting a chosen numeral is 1 over 6. And from this simple conclusion, we can reach in the following results, which are relatively interesting. Getting a 3 on the toss of a die and getting a 5 on the toss of a die are equally likely events, since the probabilities of each event are equal. Getting an even number on the toss of a die and getting an odd number on the toss of a die are equally likely events, since the probabilities of each event are equal. And finally, getting a 1, 2 or 3 on the toss of a die and getting a 4, 5 or 6 on the toss of a die are equally likely events, since the probabilities of each event are equal. Now, it's time to learn the probability of an event in a sample space. For a discrete sample space, the probability of an event, or E, denoted as this, and equals the sum of the probabilities of the outcomes in E. Now, let's see an example about it. A random experiment can result in one of the outcomes A, B, C, or D, with probabilities 0.1, 0.3, 0.5, and 0.1 respectively. Let A denote the event A and B denote the event B, C, and D, and C denote the event D. Then, the probability of A is 0.1 plus 0.3, that equals 0.4. The probability of B is 0.3 plus 0.5 plus 0.1, that equals 0.9. And finally, the probability of C is 0.1. Furthermore, the probability of A prime is 0.6. The probability of B prime is 0.1, and the probability of C prime is 0.9. Also, because the interaction of A and B only contains B, the probability of interaction of A and B is 0.3. Because the union of A and B contains A, B, C, and D, its probabilities is 0.1 plus 0.3 plus 0.5 plus 0.1, that equals 1. And finally, because the interaction of A and C is the null set, its probability is 0. Now, let's see another example which is combined with combinatorics. Consider the inspection described in the last example I talked about in the probability and combinatorics video. From a bin of 50 parts, 6 parts are selected randomly without replacement. The bin contains 3 defective parts and 47 non-defective parts. We are interested in the probability that exactly 2 defective parts are selected in the sample space. The sample space consists of all possible unordered subsets of 6 parts selected without replacement. As shown in that example, the number of subsets of size 6 that contain exactly 2 defective parts is 535,095, and the total number of subsets of size 6 is 15,890,700. The probability of an event is determined as the ratio of the number of outcomes in the event to the number of outcomes in the sample space for equally likely outcomes. Therefore, the probability that a sample contains exactly 2 defective parts is 535,095 over 15,890,700, that equals 0.034. A subset with no defective parts occurs when all 6 parts are selected from the 47 non-defective ones. Therefore, the number of subsets with no defective parts is 47 factorial over 6 factorial times 41 factorial. And the probability that no defective parts are selected is 10,737,573 over 15,890,700, that equals 0.676. Therefore, the sample size of 6 is likely to omit the defective parts. Now that the probability of an event has been defined, we can collect the assumptions into a set of axioms of probability that must be satisfied in any random experiment. The axioms ensure that the probabilities assigned in an experiment can be interpreted as relative frequencies and that the assignments are consistent with our intuitive understanding of relationships between relative frequencies. Remember, the axioms do not determine probabilities. The probabilities are assigned based on our knowledge of the system under study. However, the axioms enable us to easily calculate the probabilities of some events from knowledge of the probabilities of other events. Now, it's time to get familiar with these easy but important terms. This term says the probability of the sample space always equals 1. The property that the probability of S equals 1 is a consequence of the fact that an outcome from the sample space occurs on every trial of an experiment. Consequently, the relative frequency of S is 1. This term says the probability of an event must be between or equal to 0 and 1 in any circumstances. And this term says for 2 events, E1 and E2, that has no interaction, the probability of the union of E1 and E2 equals the probability of E1 plus the probability of E2. With the above axioms, we can reach in the following rules which can be helpful in solving questions. In probability, an event and its opposite have a relationship with each other, and that relationship is the probability of E prime equals 1 minus the probability of E. For example, if the probability of the event E is 0.4, our interpretation of relative frequency implies that the probability of E prime is 0.6. Furthermore, if the event E1 is contained in the event E2, in other words, E1 is a subset of E2, then we have this statement that says the probability of E1 is less than or equal to probability of E2. And that is done. Congratulations! Now you know some information about probability and its rules, and you can start solving complicated problems with the help of them. At last, if you liked the video, please hit that like button, and if you're interested in this type of topic, please consider subscribing to this channel, because these two keep me motivated to create these kind of content. By the way, if you have a question about this subject and anything related to probability and statistics as well as data science, comment it down in the comment section. I will answer them as soon as possible. I hope this video helps you a lot, and until the next video, happy learning!